Welcome back to your favorite engineering mechanics class, for which you already learned a lot about support reactions and how to calculate support reactions. But we need to take it one step further and need to learn a little bit more about support reactions in the context of structural stability and statically determinate systems. So today's lecture revolves all around statically determinate systems, or the idea about statically determinate systems. You already dealt with statically determinate systems, but you probably were not aware of that. And so today my goal is to actually define what structural stability is, so that you will understand why we have dealt with statically determinate systems, and so that you can identify statically determinate systems. And that is so important because when you face a statically indeterminate system, you have to understand and know why you cannot solve them. So another part of this lecture is to talk about externally statically indeterminate systems, so that you understand why you cannot solve these systems with the method provided in this class, and why you need to pursue more knowledge in your engineering career. This is very important to differentiate statically determinate and indeterminate systems. Again, you already dealt with statically determinate systems, but you may have not known about that it's called a statically determinate system, and you may have not known why it's called a statically determinate system. So we will differentiate that today. But last but not least, our goal is, of course, to calculate support reactions for statically determinate compound systems. And the reason we can talk about compound systems here is because you understand the difference today between statically determinate and indeterminate systems. And you may think that a compound system would be indeterminate if you just look at it. But today I want to clarify for you why that is not the case. So what is a statically determinate compound system, so that you are not afraid of those. And I will show to you why you can solve these. So let's go ahead and start with stability of structures, just in a general sense. And I want to just introduce this concept by bringing in a little, let's think of this as a board. So there's a free-floating board here. And of course, every engineer in the room would say, hey, this board is just floating in space. This doesn't work. I have to prevent a few things. I have to prevent this 2D system from falling down. I have to prevent it from moving left and right, and I have to prevent it from rotating. So those three things have to be prevented. And you have done this in the past already when we talked about simply supported beams and cantilever beams. So let me take the example of the simply supported beam. If I would just show this here, I would have a support block here, and then maybe a support block here. And the layman would say, hey, the system is already stable, it's not going anywhere, but the engineer knows better that this system is not stable, although the system cannot fall down, and let's pretend it also cannot move up here, because it's anchored to the ground through these blocks. And although the system cannot rotate anymore, this system is technically free to move left and right. And you have prevented this in the past by using a pin. So let me, for example, put the pin here on the right side. So there's something that actually anchors this. And just to be sure that we understand that it's anchored, I also introduced these little connector pieces here that prevent this from going up and down. And if I were to draw this as an engineer would, then we would have a system that looks probably something like this. There's the pin on the left side, and then the roller here on the right side. And so far so good. You have seen this before, you have dealt with this. And you hopefully already put it together that the reason this is stable now is because we're meeting some conditions, right? So we have the sum of the forces in X can be equal to 0. We have the sum of the forces in Y is equal to 0, and we have the sum of the moments about the Z-axis being equal to 0. Because keep in mind, we're talking about 2D systems here. And only for 2D systems, a system would be stable if these three conditions are met. In fact, we can give this a headline and call this #stable, right? I hear it's trending today. So stable is a system that allows these three conditions to be true. But now you may say, hey, this is true for this system, but I can do other things to make a system stable too. And you're absolutely right. So let's take this to the next level and let's draw the same system again. So I take the very same beam here and I apply the very same support reactions to it. So let's say I have a system here, and then I have another support here and one support here, and I'm not drawing these blue connectors anymore. But what I can do now is I can add another support. So let's say I'm adding another support right here. And of course, the system now is actually more stable, right? So this system is more stable than this, and this is still true. So engineers need to understand the difference between this system and this system. If we were to draw this like engineers do, then of course the system would look very similar to what you have seen before, but with one added support reaction here. And be careful, this support here sits underneath the beam, so it's not a circle through, right? So please understand that this here sits only underneath the beam and not in the beam. That makes a difference, as you will see later throughout the lecture. But now we can still fulfill these conditions, but we have one support reaction more. And as you will see in a little bit, you can actually not solve this system with the methods that we have. And maybe you can already guess why that is. But let's continue our thinking before I tell you why that is. So I can, of course, take the very same system again and make it even more stable. So let's do that. So I have a system that now looks like this, which is exactly the same as we had before, but I will make it even more stable by adding yet another support here. And that system, of course, is even different from the one before. So now the system would look something like this. And that, of course, makes the system more stable. If you want to think about this from a standpoint of deflection, you probably understand that this system here deflects the most if you put a force on it. So let's actually pretend we have a force sitting somewhere on there. So this force, of course, would deflect this system very differently than this system, for example, or this system. So this would just start to bow down, whereas this one here would bow down here, and then here you would actually have an uplift, if you will, or like an upwards bending. We talk about bending much later, but you understand that this support here changes how this entire structural system responds. And the same is true here. So this support here now adds some different behavior. And so engineers really have to define that, and engineers have to also know, hey, how do we think about this in terms of stability? Let me give you one other extreme, of course, just to see the other side of the equation, or the other portion that we talk about here. So we talk about stability, and of course I can have a non-stable system. So for example, let's say I have a system that looks like this. That would be not stable at all. So that is it, right? And so this would be unstable or understable or whatever you want to call it. In fact, engineers would probably call this system kinetic. It's a kinetic system, right? So this would be kinetic just because it can move. While it cannot fall down here and it cannot move left and right here, it could totally rotate downwards. So the system would actually be allowed to rotate here, and therefore it's a kinetic system. Whereas the other ones are all stable, but they are all stable in a different way. So engineers need a way to define that. And the way engineers do that is by calling this statically determinants. So this is a statically determinant system. Let's write that on the side. So this is statically determinant. Whereas the other systems are actually statically indeterminate, right? So statically indeterminate. And the problem is that the second one here is also statically indeterminate. And of course, you already understand that it's not good enough to differentiate only between this and this one. and have these two say the same thing, if you will. So this is actually what I would call stable or overstable by one, right? So let's put this in layman terms here on the right side maybe. So this is overstable one time, whereas this here is overstable two times. And again, this is not what an engineer would say. An engineer would actually say, hey, this is statically indeterminate to the first degree or to the second degree. So the first system here is actually statically indeterminate to the first degree. And the second one then here would be to the second degree. So in other words, you count the overstability and you make sure that you have this condition taken care of first, or these three conditions are taken care of, and then everything in addition to that is an overstability. And engineers don't call that overstability, they call that statically indeterminacy. So let's draw one last system just so that we understand how this actually applies. So I'm going to draw a little bit of a longer beam here, and I'm going to add some random supports to that just to play the game further. So for example, I have a support here now, which again, keep in mind, it shows that it's up and down and left and right is what these are. And maybe I'll put one here, and put one here. And I encourage you now to go ahead and pause the video and think about how many times the system is overstable and how you would draw it as a rigid body, as it is here in this column the case. So go ahead and draw that. I will do that for you in a second, and I will also define how many times it's statically indeterminate, but maybe you can already do that on your own. And of course you did. So it is no surprise when I now show you that here we actually have, let's say, a pin, right? And then on the other side we have a pin as well. And don't be fooled by that pin. That of course already, this system here would already be overstable because we have one more support reaction than we need. But to copy what we have on the left side, it would look something like this, which I need another one here, and then I need another one right here. And by the way, if you are confused about this block and this block here and then this symbol, please keep in mind that the symbol, the pin on the right, is nothing else than a system that looks like this. So I could have a roller here and a roller here. That would be equivalent to a pin. So two rollers here, they prevent left and right and up and down. This would be equivalent to a pin here. But now count your support reactions for now at least. So we have 1, 2, 3, let's say, and that would already be a stable system. But now I have 1, 2, 3, 4 additional support reactions, and so therefore this system would be statically indeterminate to the fourth degree, right? So this system here on the bottom is statically indeterminate to the fourth degree. Why? Because I already fulfill my equations here and my conditions, but I have 4 additional support reactions. One here, one here, one here, and then one of the other ones on the outside, if you will. You could also do it differently, by the way. So let me use a different color for that. So I could, for example, say, hey, I have 1, 2, and 3, and then everything else is redundant or makes it more stable. It's not redundant, it actually makes it more stable. So everything that has not a green line to it right now, that would also be overstabilizing the system. And now I invite you to think about this. Why were you able to solve support reactions for systems like these? You have done this already in your homework, but why would you not be able to solve these systems? And the answer is actually on this page here right now. And of course, I'm not telling you too much if I say that this is the real reason here. So the reason you can solve these simply supported beams so far only, and not these systems below is because you have three equations, right? Or three conditions. And when you want to solve three equations, you can solve to a maximum for three unknowns. And that's exactly what you have. You have one unknown here, one unknown here, and one unknown here. So if you have any more unknown, these conditions are not enough anymore to solve the system. And so if you have more than three unknowns, you need initial conditions or boundary conditions, depending on what system you would solve for. And that technically goes beyond the purpose of this class, but since we're talking about stability here, let's quickly conceptually talk about how you would analyze this. So, for example, if I have a force acting on this beam here as well, then I could treat it like this beam above here first, and I could calculate what the deflection at this location here would be. So for example, here's the support, so I want to calculate what would be the downwards deflection. And again, we can only do this conceptually because in this class we have not discussed yet how to calculate deflection. It's way beyond the purpose of this class right now. But if you were able to calculate how much this deflects downwards, if the support is not there, then you can use the boundary condition of the support, which says, hey, the deflection here must go back to zero because the support does not allow this to go down, so that you can actually calculate how strong the support has to be to bring it back into the zero position. And you can do this multiple times. This is conceptually how that would work. But what's important for us to understand is that we so far can only solve three support reactions because we have these three equilibrium equations. But there's a system or a type of systems that actually remain statically determinant, although they have more than 1, 2, 3 support reactions. So today we will see some systems that have maybe 4 or 5 support reactions, but they remain statically determinant and they are not statically indeterminate. But before we move on to those problems, let me give you one word of caution about something that you sometimes read in the literature. Some people in the literature say, hey, if you want to find out how many times it's statically indeterminate, all you have to do is count support reactions and then subtract 3. So the logic in the literature is, hey, this allows you to find 3 unknowns and then you count. And this works for all the systems that you have seen here, right? So for example, if I count here, I have 1, 2, 3, 4, 5. And then I subtract 3, so that leaves me with 2 unknowns. And that's true and that works, but there are sometimes systems that have more than 3 support reactions, but they are completely useless. So for example, if I were to draw a system here that looks like this, and I have a support here, and a support here, a support here, and a support here, then you would probably agree with me that we have 1, 2, 3, 4 support reactions. And if I were to count this and subtract 3, then I have statically indeterminates of 1. But that is completely useless because the system here is also kinetic, right? So this is also a kinetic system. And therefore, I cannot use this as a structural system. And so I always caution students to not use any formulas. So for example, the formula that they list in the literature, of course, is n minus 3. But sometimes it doesn't work. And there are other systems where that doesn't work, which I will not allude on to further here because we haven't covered some other topics. But I just would caution you to not use simple formulas. It's better to have a physical understanding of the system. And talking about physical understanding of the system, let's actually move on to the statically determinate base systems. Now there are actually base systems that we can use to define statically determinate systems. So there are 3 systems available to us that are always statically determinate, and we can use them to build up other systems. So we would call these statically determinate base systems. And you already dealt with 2 of them. So let me draw those 2 for you. And in total, we have 3 of them actually. So right now, I'm only going to give you the 2 that you are already familiar with. And one is the simply supported beam, because that one is a stable structural system with 3 unknowns. And then we also have the cantilever beam, which you already very familiar with thanks to your homework. But let's understand that this here is called a simply supported beam. Simply supported beam. And then we have the cantilever beam. And you probably understand now why this is called a simply supported beam, right? Because this is as simple support as it gets without being a kinematic system and without being overstable. So we call that simply supported. And you also understand that these systems, of course, fulfill the 3 conditions: the sum of the forces in X, the sum of the forces in Y, and the sum of the moments. All of them are equal to 0. Now there's a third system which I will only draw here for your reference. We will talk in a little bit more about this, but that is a beam that looks as follows. It is kind of resembling a roof structure. And what's important about this beam is 2 things, as you will understand in just a little bit. It is having a hinge here on the top. So this here is a hinge. And now I will actually introduce a pin here, and you know that this has 2 support reactions. And I want you to think about what would happen if I were to install a roller here now. So if I have a roller here, which would look like this, then you probably understand that if I apply a vertical force here, or I push on this anywhere on the roof, this would slide out to the side. So this would not be a stable system. And this is exactly where we want to go and what we want to understand today. We want to understand what happens if we actually turn this into a pin, because then, according to our definition, we now have 4 support reactions that we have to take care of, right? So we have 2 here and 2 here. And according to everything we learned so far, we would not be able to solve this. But as you will see in a little bit, the hinge actually gives you another boundary condition. And we will talk more about the hinge as a boundary condition on the following page. But for now, let's just understand that this is called a hinged, simply supported frame. And you understand where the name is coming from. So it's the simplest form of support to a frame that is hinged. Because as I said before, if I would have a different support reaction here, then this could slide out. Or if I make it more stable, it would just not be simply supported anymore. It would not be the simplest form. But the reason these 3 base systems are so important is because you can use them to form many other compound structures. And we will see that as well on the other page. But let's for now understand that we have 3 base systems. And these are the 3 statically determinate base systems. And 3 is the number here. We only have 3, no more, no less. And we can combine these to form many different other structures. But to understand that, we need to talk about hinges, because they are used here and also when we connect them. So let's move on to the next page and talk about hinges. Let's take some time and talk about hinges before we continue to talk about compound systems. So what is a hinge really? Of course, we are all familiar with that when it comes to our door in our home. But the way engineers draw them, if they connect, for example, 2 rigid bodies, it would look something like this. So we have a circle here that symbolizes a hinge. This is the hinge. And what does the hinge do? Just as it does in your door at home, it allows rotation. And this is where the definition lies, right? So allows rotation. And remember from our basics in this class when we talked about the warm-up that rotation is very closely related to a moment, right? So a moment, what was a moment? A moment is restricted rotation. And so if you have a hinge which allows the rotation, then you cannot have a moment anymore, right? So the moment has to go to 0 at a hinge. And this is really what you need to understand. It's difficult to understand this just by definition, but this will become clear throughout the class. That at the hinge, so at the hinge, the moment has to be 0. And let's be very clear here. Sometimes in the literature you read that the sum of the moments is equal to 0 at the hinge. And I don't know which color to use or like how to make this more important, but this is not, right? This is not the sum of the moments is equal to 0. So this is true, but it is very different than saying that the moment at the hinge is equal to 0. Let me clarify the difference. So the sum of the moments for static systems is always 0 at every location. It's 0 here, it's 0 here, it's 0 here, here, anywhere. But the moment to be 0 is only true at the hinge. So the correct way to write this, so instead, the moment at the hinge is 0. And therefore, we would say that mh is equal to 0. It is a very important differentiation to leave this sum of the moments out. It's that the moment at the hinge is going to 0. You will understand this more when we talk about internal forces, because technically the force at the hinge, or the moment in the hinge, is technically an internal moment. And of course we haven't talked about this, but for now please understand that the hinge allows rotation, and because it allows rotation, let's say this can move in this direction and this direction, and this can move in this direction and this direction. That is why we have another boundary condition, and the boundary condition is the moment is equal to 0. This is an initial condition we always had. This does not help us at all, the sum of the moments being equal to 0. We only get help through the hinge if we understand that the moment at the hinge is equal to 0. And that now allows us to move forward to compound systems, because now I can use hinges to actually connect systems. And that's in fact what you saw already for the simply supported frame, the simply supported hinged frame, if you will. So let me actually start by talking about that one. So here's why that works. So the way it looked was something like that. And it really doesn't matter what the angle is or what the dimensions are. Conceptually speaking, the reason this system works is because, yeah, you have 1, 2, 3, 4 support reactions, but you also have another initial condition, which is the moment being equal to 0. And so you can, for example, take the sum of the moments about this point and set that equal to 0, and you can take the sum of the moments about that point and set that equal to 0. And so you actually end up with two equations with two unknowns, because you have this boundary condition. And this applies to other systems as well. So compound systems, I'm going to leave room for another easy compound system up there. But for example, I could have another compound system, which let's say looks like this. I have one rigid beam on the left and another rigid beam on the right, and I connect them with a hinge. And this right now would not work. I need to support it. And let's say here on the right side, I put a cantilever support. But of course, you paid attention and you know that this hinge here allows rotation. So therefore, this system here would fall down now. And therefore, this part would currently be kinematic. What can I do to stop it from being kinematic? I can just support it anywhere. I just choose to do it at the end here right now. So I have one more support on there. And now if I count my support reactions, what do I have? I have 1, 2, 3 support reactions on the right side and 1 support reaction on the left side, gives me 4. But I also have that the moment at the hinge is equal to 0. And therefore, that is my initial condition or my boundary condition, which allows me to solve these 4 support reactions. This is true here as well. So let's write down that here I also have a hinge, and I know that the moment at the hinge is equal to 0. So these are two kinds of statically determinate compound systems, and you now understand why they are statically determinate, and also why they're compound systems. So they're statically determinate because you can still solve them with equilibrium, but you have compounded the systems. For example, here you have a cantilever beam that is connected to a simply supported beam. And you may think, how is this a simply supported beam? It's clearly missing support here, but that is not true. Why not? Because the cantilever here provides the support for the simply supported beam here. So this is a cantilever on the right side and is simply supported, and they are connected through a hinge. Like I said, there's other systems as well. Let's draw yet another one, like one complicated one, I guess. And let's say we have a hinge here and a hinge here. So I need my dashed line because it's always rigid bodies. And of course, I need support reactions as well. So let's say here I have a hinge and here I have a hinge. And I bring in a support, let's say here. And then I have a support reaction here and a support reaction here. And this now is a way more complicated system, but you can see that you can still solve them because you have two unknowns to the right side of this hinge and two unknowns to the right side of that hinge. And why is that important? Because, as you remember, m at hinge is equal to 0, and m at the hinge is equal to 0 here as well. So what you can do, conceptually speaking, is you can take the sum of the moments about this point, and you can, for example, release this system here and find 1, 2 support reactions. That would give you one equation with two unknowns, and let's call that equation 1. But you can also have your equation 2, because you know that your moment there is equal to 0. And in this equation, you have the very same 1, 2 unknowns. And so you have two equations with two unknowns, which you then can solve. And you can find the answer. And once you have those solved, you could, for example, go ahead and take the sum of the moments about this point here and have a third equation. And then you would have a third unknown in here. And that would allow you to solve the system. Let's look at this system here in a similar fashion. How would we solve this? And to make it a little bit more relevant or easier to follow, let's actually add a force on it. So let's pretend that I, for example, have a force acting here on the system. Let's call this F1. Now, how would I solve the support reactions? Correct, you guessed it. You know that your moment at the hinge is equal to 0. So therefore you can create subsystems. You can create a right subsystem, which won't help you in this case much. But you can also create a left subsystem. So let me draw that. So let's say I do what I call a cut cloud. So I cut this system. I release this system from the structure. And now I know that my moment here is equal to 0. That means that everything in this cut cloud here has to balance at this point. So whatever F1 is causing in rotation here at this point has to be balanced by RAY. So let's add actually an RAY here. So let's call this RAY. And hopefully you can see that RAY times its distance to the hinge has to be in balance with F1 times its distance to the hinge. And this is true because here rotation is allowed. And so this left subsystem has to be in balance. And therefore I can solve this. But then the next confusion comes in. Let's say you now already know what you have. Let's say this here would be 10 Newton, for example. Then the students often are confused. What do I do with that information? There's a hinge here. How do I calculate these remaining support reactions? And the answer is, once you have this, you do not worry about the hinge anymore, because the entire system has to be in equilibrium as well. So RAY, F1, and everything else that would potentially act on the structure would have to be in equilibrium with the support reaction. So for example, if you were to take the sum of the forces in the y direction, then you know that you have an R, let's call this by here. So RBY plus RAY must be equal to F1, right? So this would be the equation for this entire system. And likewise, this moment here, MA, about the z-axis, so MA about the z-axis has to be in equilibrium with everything that acts to the left of the system. There's no exception to that. Again, I see students often initially being confused by the hinge here, but the trick is, once you've figured out one unknown, the hinge does not matter for now. At least as long as we talk about support reactions. Later on, when we talk about internal forces, of course it has an impact. But again, we'll talk more about that later. So for now, don't worry about this. You find your subsystems, you find the side that you can solve easier. So for example, the right subsystem here, you could have not solved that. So if I were to cut the system here and I call this here system 2, that is something I would have not wanted to solve initially. I would have want to solve subsystem 1, and once I have all my answers from subsystem 1, I can apply them to the entire system. So maybe for clarity I should even add like a third system here. So that would look something like this. So I have a third system, and that also needs to be in equilibrium. So if I would have solved this type of structure, I would have first solved subsystem 1 and then system 3, if you will. And I kind of did the same thing over here, and depending on how the systems look like, of course the systems may be very different, so don't be fooled by just understanding one type of system. Every system is different, and my experience in the classroom is that if I change one length or one dimension, or I put the hinge somewhere else, sometimes students already get confused, but the concept is always the same. You try to break it down into subsystems that you can solve with the information that your moment is equal to 0 at the hinge, and then you apply it to the rest of the system. Now, last but not least, I told you that I left some space here for the last simplest compound system, so let's go ahead and draw that just for completion. There's one more system that is technically also a compound system. It's really not a difficult system, and it's called a simply supported beam with overhang, and that looks like this. So we have a support here and another support here, and now we have overhangs on both sides. So why are these compound systems? Because I have a simply supported beam, and the overhang is technically a cantilever, and here in this case I have it on both sides. So this would be called a simply supported beam with overhang. And so that's why it's called a compound system. But in conclusion, compound systems that are statically determinant are always systems that are made up from various different systems that are statically determinant in a sense. And so you can now identify these systems, and you can, of course, understand why you can solve them. Which takes me to our last section here for the lecture today, which is statically indeterminate systems. So let's move on to statically indeterminate systems. Of course, we already talked about statically indeterminate systems, but now that we have a much better understanding of why we can calculate statically determinate systems and why not statically indeterminate systems, and what makes a statically determinate system, it's also good for us to formalize statically indeterminate systems. So statically indeterminate systems, as we alluded to before, are systems that cannot be solved anymore with our 3 equations and our 3 unknowns, and also we don't have enough boundary conditions to solve it simply based on our free body diagram. So for example, this would be the very first indeterminate structure that we cannot solve anymore, because it's not a compound structure, because we have 1, 2, 3, 4 support reactions, but only 3 equations that we can solve them with. And so that does not work. And of course, we can draw structures in any shape or form. In fact, let me actually make some random shapes up here. So for example, let's say I have a structure that looks like this, and then maybe like that, and I have a support here, and then maybe I have a support right here, I have a support right here, and a support right here, and maybe I even have one under a random angle here. And so now the one thing that you need to understand about statically indeterminate systems in this class is how many times is it statically indeterminate. So can you guess which the degree of statically indeterminacy is for this system? Go ahead and do it. And after you finish pausing the video, I'll solve it for you. I have 1, 2, 3, 4, 5, 6, 7, 8. And so this is to the 5th degree, right? So 5 times statically indeterminate, so 5th degree. And so you need to be able to identify how many times is it statically indeterminate and why you cannot solve this. Let's make 1 or 2 more systems that are statically indeterminate. So for example, I can have a cantilever that may look like this. And then I weld another structure to it. So let's say something like that. And maybe I even build a system on there just to teach you one more thing about statically indeterminacy. And let's say that looks like this. And so now be careful, right? Because here you actually have a statically determinate system on top of a statically indeterminate system. So what I'm trying to tell you here is that this is your hinged, simply supported frame that is statically determinate, and it just sits on top of the structure. So this is just adding forces to the system. So this is not counted in my statically indeterminacy, but I have 1, 2, 3, 1, 2, 3, 6, 1, 2, 3, 9. And so this is to the 6th degree, right? And I want you to understand that all these systems here are statically indeterminate due to their support reactions. And support reactions are technically external forces. And so therefore we call this system externally indeterminate. Right? So they are externally indeterminate, and that should tell you something that is beyond the purpose of this class, but later on in your engineering career, you might find that there's not just externally statically indeterminacy, there's also internal statically indeterminacy. And just to give you a flavor of what that means, so let's say you have a cantilever beam that is standing like this. So this, of course, you know, is statically indeterminate because you can calculate it. And now to explain to you internal statically indeterminacy, I want you to consider the following. So I'm going to weld something to this cantilever beam. So this is a rigid frame. Think of it as being made from metal. And as of right now, this is a completely statically determinate system because everything is free to move and there's no restriction. But as soon as I come in and weld this together, so let's say I weld something on here and I rigidly connect this, I have a problem that engineers have to address, and that is that now this system here is connected rigidly, which transmits the forces from one part of the structure to another one. And you can see this is kind of like a closed frame. So think of heat being added to the system. What happens if you add heat to it? Every part of the structure wants to expand. It wants to become longer. And therefore, the forces will actually transfer from one part of the structure through the welding to the next part. And so this would be outside of what we need to understand here. This part is not something we talk about, but this would be an internal statically indeterminacy. So this is an example where you can actually have a statically indeterminate system, not due to its support reaction, but simply due to the fact how it's connected within itself. So you need to differentiate internal and external systems, or statically indeterminate systems. And in this class, you don't even have to calculate statically indeterminate system, but you have all the knowledge you need to understand how often a system is statically indeterminate, or better said, to which degree. And this is part of this class. You need to understand how often the system is statically indeterminate. But with that said, we now have covered everything we need to know about connected systems or compound systems, and we understand statically indeterminacy and statically determinate compound systems, so that now we can actually go ahead and apply the knowledge that we developed here for these systems to example problems, and we can now go ahead and calculate compound systems that are either not hinged or hinged together. And we will do that in our next upcoming problems. So here we see our very first compound statically determinate system, and of course by design this is a very simple compound structure. But although it's very simple, I'm not trying to insult your intelligence here or anything, but I just want to make sure that we talk about it quickly so that everybody has a chance to get on the same page and to understand this. If this is too easy for you, just move on, no harm done. In fact, you will see in a second why this problem can be so simple. One reason for that is because it's a symmetric system. It's symmetric over the center line, and I have two vertical supports that carry the same amount of load on both sides. So one easy way that is not very educational would be to just cut the system here in half and then say everything on this side is carried by RBY and everything on the other side is carried by RAY. And so you could do this real quick. You could say, hey, the sum of the vertical forces that is going down, and then divide that by 2. And that would be your force carried by, for example, RAY, which is also equal to RBY in this case. But we want to learn something here. So let's actually go through the process and see how we would solve this with free body diagram and with the moment equation. I'm just going to do one support reaction here for the purpose of this example. So my free body diagram is, of course, a rigid beam which has load acting on it, which there's a lot of load acting here and then a little bit less load here, and they are all pointing downwards. So this would be my load case. Of course, I have to bring in my unknowns. So I have my RAY here, and I have my RBY here, and of course you also know that I have an RBX in this case. And just so that I don't have to move up and down here, so this is 300 pounds per foot, and then here I have 200 pounds per foot. And of course here I also have 200 pounds per foot. And now I can go ahead and calculate my support reactions by taking the sum of the moments about any point. So for example, if I want to find RAY, I would do that by the sum of the moments about B being equal to 0, counterclockwise positive, and 0 would be equal to, I always start with my unknown, minus RAY times 8 feet. And then I have to consider my first 200 on the left side. And again, I understand this is not how an engineer would do this in real life, but we're doing this for education, right? So I just want to dissect it into each of the individual components. So I start with the 200 here on the left. So that, of course, turns about this point here counterclockwise. Sorry, it turns counterclockwise. Therefore, it's positive. So plus 200 pounds per foot multiplied by 4 feet. That's the distance it's acting over. And now I need a lever arm, and the lever arm, of course, is from here, from its center to here. So this is 4 plus 4 plus 4 halves. So really what I'm looking for here is 4 over 2 plus 8, let's say, feet. And that is the lever arm of the first force. And now I have the 300 that also rotates counterclockwise about this point because it's lumped here in the middle. So the 300 turns also counterclockwise. Therefore, it's positive 300 pounds per foot multiplied by 8 feet in this case, and then multiplied by 8 over 2 feet. That's the lever arm in this case. And last but not least, I have the 200, and notice that the arrows are pointing downwards just as they did over here. But now, because this is to the right of the support, I turn clockwise. Therefore, it's a negative component. So I have minus 200 pounds per foot. And that is also acting over 4 feet lengths. But now the distance is from its lumped force to the support, which of course is half the distance it's acting over. So we would look at 4 over 2 feet. And that is the entire equation. And this is the only educational part we have to go through in this example so that you understand which part of the distributed force rotates about which point. But now I can solve the problem for you, and I can tell you that RAY is equal to 2,000 pounds. So 2,000 pounds. And that is a result. And by the way, that result due to symmetry is also equal to RBY. And in both cases, they are pointing upwards, right? So I identified that. And that almost completes my entire example here. The one thing I probably should also say is that RBX is equal to 0. That's technically a result as well, because now I have 3 support reactions, which of course after this lecture, you know now why we always have to report 3 support reactions. So this completes the entire example, and I think you can probably agree that we could have used simple symmetry, and no engineer who ever paid attention in engineering mechanics would go through all this effort down here. Obviously, it's not a lot of effort and not very difficult, but you probably would have said, hey, it's a symmetric system, so therefore 300 times 4 plus 200 times 4 would be carried by the support here on the right side, and then the same here on the left side. But this is the educational portion that sometimes students initially struggle with, but it's so important to understand this. So we went through the educational process of understanding which force acts with which lever arm, so that you can solidify that knowledge before you take any shortcuts that you can definitely take later on in your exams. You can take shortcuts just using symmetry, but you have to clarify how that is working properly, and you have to communicate that properly so that it can be understood where you're coming from. But this completes this example, and we can now move on to slightly more complex problems. So here in this problem, you can see that we're starting to do real mechanics. We have a problem that is a compound, simply supported beam on the left with a cantilever on the right. And I think the picture speaks for itself, that we have a fixed support here, and then we have a roller here, and this symbolizes the hinge. So you see there's literally like a pin point through into the page that connects the right part of the system to the left part of the system. And so rotation is allowed to happen here, but the pin prevents vertical and horizontal movement. And so we can actually solve this system. Of course, first we have to draw the free body diagram. Before we do that, note that we have a distributed force here, an evenly distributed force of 40 kilonewton per meter, and then we have 200 kilonewton acting under a certain angle, 75 degrees here. Now, before I go ahead and draw the free body diagram, let me actually copy this into a symbolized version of the structure so that you understand where we're coming from in terms of support and hinge, and so that you can follow how these systems look like when we put them on paper. So first on the right side, I have a cantilever support or a fixed support, and then I have a hinge here, that is my circle, and then last but not least, I have a roller here on the left side. And this is clearly not a free body diagram, because a free body diagram has forces in it and not symbols. So I'm going to copy this now into my free body diagram, which of course still has the dashed line because it is a rigid body. But now I have to be careful in terms of how I translate my forces. So let's call this here RAY, and I assume that to be upwards. Then I have R, let's call it CY. I have RCX, and I have MC about the Z-axis. And I assume that to be counterclockwise right now for no good reason, right? This is just an assumption, and I will deal with that later. I have also external forces on the system. So I have an evenly distributed one and a concentrated one, which I break that down into two components, into a vertical component and a horizontal component. Those happen to be 200 sine 75 and 200 cosine 75. And then my evenly distributed force is just nothing else than the 40 kilonewton per meter. So 40 kilonewton per meter. And by the way, this is also in kilonewton here. All right. So now what can I do here to solve the system? I can break it down into subsystems, and you already know that you have to do that at the hinge. So the only thing you're probably struggling with now is, do I take the right subsystem or the left subsystem? And the answer in this case is very easy. I would take and start with the left subsystem because I just have one unknown in that subsystem. And in fact, if you just look at the system here, the left subsystem, you can probably very quickly identify how strong RAY has to be, because you already know what force is acting downwards and what happens if you remove RAY. If you remove RAY, which is really what you do in the equation that I will show you in a second, but if you remove RAY, then the 40 kilonewton per meter over a distance of 4 meters and a lever arm of 2 meters is really rotating downwards. But the force that is rotating downwards is 40 kilonewton per meter times 4 meters. So that would be 160. So let me just for now add this force and say that there's an F resultant that's really acting here. And I really don't like to add these here, but it gets the concept across. So this would be 40 times 4, right? That would be 160. So there's something pushing down with 160 kilonewton. And yes, it has a certain lever arm, but I don't even care about this lever arm being 2 meters long. The only thing I care about is that this lever arm is half the length that RAY provides. So there's 160 rotating down, and I have to push back to keep it in equilibrium and to not rotate about this hinge here, because keep in mind that the moment at the hinge MH is equal to 0, and so everything has to rotate about that point. And if 160 with 2 meter is rotating about this point, then due to twice the distance for RAY, I only have to provide half the force of the 160. So with a little bit of experience, you can already identify this to be 80 kilonewton. Of course, as a beginning engineering student, I definitely have to practice that, and that's why I will show you how to really calculate this. But maybe it already makes sense to you that if this system here rotates about this point, the 160 must be in balance with the 80, and that can only be true if the distance between RAY and the hinge is twice as much as 160 to the hinge. Or vice versa, depends on how you look at the logic. But if I would know nothing about this and I would just learn this concept, what I would have done is I would have wrote out that RAY is calculated through the sum of the moments about the hinge being equal to 0, counterclockwise positive, and 0 is equal to minus RAY because it turns clockwise, right? And that was 4 meters plus 40 kilonewton per meter multiplied by 4 meters multiplied by the lever arm, which is 4 over 2 meters or 2 meters. And that is all I need. Technically, so really technically speaking, there's also plus m in the hinge, but that is equal to 0. So therefore, this equation works. So because you have this condition here, m at the hinge is equal to 0, you can solve it as is. And so if you rearrange this now, you will find that RAY is nothing else than 40 times 4, which is 160 kilonewton, and that then times 2 divided by 4, right, which is nothing else than 1/2. So that is equal to 160 times 1/2, which is really equal to 80 kilonewton. And now the problem is no different from anything you have seen before. So you can now think of the rest of the system as a cantilever, at least for the purpose of calculating the support reactions. So the last thing you have to do now to find, for example, RCY is just establish equilibrium in the vertical direction, and you completely can forget for now, this is different later on in the class, but for now you can just forget that there's a hinge there. So let's do that. So let's say that we want to find RCY, and I do that by the sum of the forces in the y direction being equal to 0, upwards positive. 0 is equal to plus RCY minus 40 times 4 times nothing, because we are not multiplying this by a lever arm. So in fact, I should probably erase this for clarity, and I should add units here. So 40 kilonewton per meter multiplied by 4 meter. That's the F resultant, the 160. Now there's also the negative 200 times sine 75. And then last but not least, I need to add the 80, which comes from RAY, right? So plus 80. And this is really RAY. And that is also in kilonewton. And so now I can solve this for RCY. So RCY is really equal to 273.2 kilonewton. And this, of course, is a result, just like my 80 above here. So now I have my vertical support reactions, and I can continue with my next support reaction, which is the moment at the support C. So what I'm looking for is MC about the z-axis, and I find that by the sum of the moments about point C, counterclockwise positive, being equal to 0. And 0 is equal to, I always start with my unknown, and notice that I assumed it to go counterclockwise. Therefore, it's plus MC about the z-axis. Now plus my 200, and I say plus because the 200 sine 75 also turns about this point counterclockwise. So therefore it's also positive. So plus 200 sine 75, and that's in kilonewton. So I need a lever arm to that, and that happens to be 1 meter. Now, as I said before, I can just continue and pretend the hinge doesn't even exist. So I add the 160, but I write that out as 40 kilonewton per meter multiplied by 4 meter, and that is F resultant. And I have to find a lever arm, which is 4 halves plus 1, if you will, and that is in meters. And that rotates as well about point C, so it rotates this way around, which is counterclockwise, therefore it's positive, so I add a positive here. And then I have one last thing, which is RAY, so that pushes upwards, so minus 80 kilonewton meter, so minus 80 kilonewton, sorry, not kilonewton meter, multiplied by 4 plus 1 plus 1, so multiplied by 6 meters. And now I have all my forces that I need to consider, or all my rotations that I need to consider, and I can calculate that MCZ is actually equal to, be careful, it's minus 353.2 kilonewton meter. And what the minus means in this case is that I was wrong. I assumed it to go counterclockwise, so therefore it's in reality clockwise. So clockwise is what that means. And that is a result. And this makes, by the way, perfect sense, right? Because if the system is supported here, and there are forces pushing down, they want to make the system go down here, and here you have to rotate it back. It has to rotate this portion back up. Otherwise, you would just, if you rotate counterclockwise as indicated here, you would just add to what this force is doing and what this force is doing, and the whole system would continue to rotate. But you have to balance it, so it makes perfect sense to actually set this in the other direction. So let's double underline that result as well. And by the way, just to be complete here, I also need to indicate that this is going up and this is going up. So last but not least, I need my horizontal support reaction, so my RCX. I do that by the sum of the forces in the x direction being equal to 0, and 0 is equal to minus RCX minus 200 cosine 75. And so therefore my RCX is actually equal to negative 200 cosine 75, which then in reality comes out to be minus 51.76, so minus 51.76 kilonewton. And that in reality means that the force is going to the right, so positive to the right. And that is yet another result. So now I answered the entire problem here. And notice that now we actually have 4 answers. So we have 4 support reactions, although it's a statically determinate system. But thanks to the lecture, you of course understand where that is coming from. But let's take a look at the entire problem again. So we have a system that is a simply supported beam on the left and a cantilever beam on the right connected through the hinge. There's a distributed force here and a concentrated force here, which then was always included in our calculation. But before we included all of it, we looked at only the left part of the system because we only had one unknown. We used engineering logic here first, or pretty much balance, to solve the 80 kilonewton, but we also derived it based on the moment equation about the hinge, because we know that the hinge carries a moment of 0 because it allows rotation. And once we had that, everything was a walk in the park because we did not have to change any logic. We just applied this force as an external force. It's just like a cantilever with a force of 80 kilonewton acting here. And so we were able to find the vertical support reaction, and then to find the moment at this location, we actually took the sum of the moments about that point. Why did we take that point? We could have taken any other point, by the way, but I like to take this point because it makes RCY disappear. And so if we would have made a mistake here, then this force would have also included a mistake in this calculation. And by taking the sum of the moments about point C, we completely ignore RCY and RCX as well, because both lines of action pass through that point. And so we were able to solve it, and we found that it was actually clockwise moment instead of counterclockwise, so that it can actually rotate this part of the structure back up. And of course, we cannot forget about the horizontal force. So again, 4 support reactions because we have a compound system. But this concludes this problem, and we are ready for our next example. So here we see another example of a compound system, maybe a little bit more interesting or more complex than what we've seen initially. What we have here is a simply supported beam on the left side with an overhang and then another simply supported beam. So the system really has, let's count the support reaction, has 1, 2, 3, 4 support reactions. But we also have a hinge, so we know that the moment at the hinge is always equal to 0. And of course we need to assume directions, so let's say I assume this going up, and this going up, which of course is not always true for all of them, but let's just assume that I have these forces here, and I call this RAY, RAX, RBY, and then RDY. And now I would be able to solve them, and in this case it actually doesn't matter what you do. There are 2 easy ways to solve this. The easier way, of course, is what you probably are thinking of, is you release this part of the system and you find equilibrium. And that would be definitely what I would be doing in an exam. But just for the concept, let's talk about the fact that you can also release this part of the system and find equilibrium about this point. You would have RAY and RBY as an unknown. So you have one equation with 2 unknowns, and you would think you cannot solve this. You're right. But what you can do is you can take the sum of the moments about this point as well, so that you have this entire system as the second equation, and you have RAY and RBY in that, and then you have 2 equations with 2 unknowns that you can solve. And this would be absolutely correct, but probably not the most favorable way to do it. So let's solve the problem, or I'm not going to solve the problem for you, but I will at least conceptually explain it to you. And to do that, I want to start by drawing the free body diagram with or for you. So let's go ahead and do that. So I have my rigid body here, and I have support reactions left and right. There's my hinge, and I think I assumed RBY to go up, RAY to go in this direction, RAX in this direction, and then last but not least RDY. Okay, my external forces need to be included as well. So I have my distributed force that acts all the way over here. And then I have a moment as well. And my moment rotates in this way, so clockwise, right? So 200 kilonewton meter. And then here we have once again 40 kilonewton per meter. And again, I don't need to solve the entire problem for you, but I want to at least give you an insight, and that is to find RDY, I have to take the sum of the moments about the hinge being equal to 0, and that is counterclockwise positive, and 0 is equal to plus RDY multiplied by 2 meters, so multiplied by 2 meters, and then the 200 kilonewton meter, remember we had a lecture about how moments work, and this turns clockwise, so therefore it is negative. And that's actually everything I need to know about this equation that I developed for this subsystem. And so I can now go ahead and solve for RDY. And with a little bit of practice, you could have done this without even running any math. You would have seen that, of course, you have to take the 200 and divide it by 2, which then is equal to 100 kilonewton, right? And notice that this works out because we have kilonewton meter here, and we're divided by meter. So therefore, we end up with kilonewton. And now you have the problem that you have one vertical support reaction, but still 2 unknown in the vertical direction. So it's not as convenient as we had before, where you could just take the sum of the forces in the y direction. But what you can do to find RBY is what? Exactly, you take the sum of the moments about this point, about A. So to find RBY, I can take the sum of the moments about point A being equal to 0, and of course, as always, counterclockwise positive. And then 0 would be equal to, and now I have to be careful, I need to memorize that this really did go up, so my RDY went up, so I need to include that, but I always start with my unknown, that is RBY, which is assumed to go up as well. So I say that turns counterclockwise, right? Because we're rotating about this point, so it turns counterclockwise, which means plus RBY multiplied by 2 meters. And let's just be clear where this 2 meters is coming from in this case. It's the distance from here to here. And then I add my RDY, so that is also positive, so plus 100 kilonewton multiplied by the entire length. So 1 plus 1 plus 2 plus 2, that's 6 meters. So times 6 meters. And then I have to include my 40 up here and my 200. Let's start with the 40. So I have 40 kilonewton per meter, which is acting over a length of 4 meters. And the lever arm now is equal to, be careful, I have the entire system here, so it's acting in the middle, which is exactly above RBY, so it also has a distance of 2 meters, or 4 halves in this case. So times 4 halves meters. That rotates, in this case, clockwise, therefore I have to make that negative. And last but not least, I have to include my 200, and the 200 turns clockwise, so therefore that's also negative. So minus 200 kilonewton meter, that is. So kilonewton meter. And I don't even have to calculate this out for you right now. You just find that you get an RBY. RBY is equal to something, and presumably that's really positive. So I'm going to assume that it's really going upwards in this case. You can calculate and verify this, but I'm pretty certain it will be. Now, the last thing that I now have to do is find RAY and of course also RAX, but let's actually get that out of the way. RAX is equal to 0. Don't even have to worry about that. So double underline that. And then here I have my RDY. So I have 2 results. Here I would have my third result. And so I need my last result, which is RAY. And how would I find that? I could do it either by the sum of the moments about a point, but the easiest way in this case would be the sum of the forces in the y direction being equal to 0 and upwards positive. And 0 would be equal to plus RAY, because I assumed that to go upwards, plus RBY, which of course technically I would know at this point, plus RDY, which I already know is equal to 100, so I might even plug that in here, minus 40 times 4. And that's all I need to know. This one here I already know from right here. So RBY would pretty much go into this equation. And then I could solve this and I would have found all my numbers for this simply supported compound structure, if you will, or a statically determinate compound structure. And so you know now how to interact with these hinges here and how to calculate support reactions if there's a hinge in the system that connects a system on the left side to a system on the right side. So I believe that is everything you need to know to successfully complete your homework and to move forward in this class. So let's conclude the lecture on our last page and let's talk about the description of the homework. Of course, you know best what your takeaways are and what part is still a little bit in question for you, but I encourage you to fill out these 2 boxes here so that you can really help yourself studying and better prepare for the upcoming quizzes and tests. But I will move on to the actual checkbox of today's lecture. And the first thing that we, of course, talked about was the statically determinate systems and what makes a system really statically determinate. So we can now identify these systems so that we can also understand what stability is, and in specific terms structural stability, so that you can distinguish the determinant and indeterminate systems. So I hope you remember that you don't have to calculate any forces in statically indeterminate systems, but you have to be able to identify statically indeterminate systems, and you have to know the degree of indeterminacy. So you need to understand that. And I also showed you the three base systems, right? So all three base systems, which are the simply supported beam, the cantilever beam, and the simply supported hinged frame. So you are familiar with those, and you also understand that you can use these to create different compound systems. So that is something that should sit deep in our brain now, and I hope we understand that. Once we recognize these systems, we need to know how to calculate the support reactions in those systems. And of course, we do that by using the hinge and by understanding that the moment there goes to zero. So the moment at the hinge is what really allows us to solve that, because we know that rotation is allowed, and therefore we have an initial condition or a boundary condition. And we definitely understand that this is different from the fact that the sum of the moments is equal to zero, which you sometimes read in books. So please highlight this, that this is really different. And then once you highlighted this and you understand this, please go ahead and check this off. Last but not least, we used our newly gained knowledge to actually calculate support reactions for these statically determinate compound systems. And I hope you understand that the mathematics in this class, or the procedures in this class, do not allow us to go beyond determinate structures, right? So we can, of course, deal with compound systems, and we can deal with any determinant system, but we cannot deal with statically indeterminate systems. So this is something that I just introduced to you in this class, but I want you to understand it. You do not have to calculate it. The only thing you have to calculate in this class is determinant system, and the way we dealt with it today were the compound systems. So those are our checkpoints, and we are now ready to move on to talk about the upcoming homework. As you can see, our last support reaction homework here in the lecture series deals with compound systems, or hinged beams in this case. And maybe I had a good day, otherwise I cannot explain why we only see 4 problems here and not 6, but you are very much welcome. So you get a short break here from all the work you have to do. But let's take a look at the upcoming homework problems here, although it's only 4 of them, and hopefully you won't be too bored when you only have to solve 4 of them. So the first one here asks you to find, of course, the support reaction as all of them, and what you have is a hinge at B that is symbolized in this case for a steel beam here in this case, and we have a fixed support on the left and a roller on the right. There's a concentrated force and a distributed force. I don't think this should be a big challenge after today's lecture, and we can already move on to the next problem. And for the next problem, you get a very similar beam, but the one additional challenge that we added here is that the distributed force, W1, actually passes from the left side to the right side over the hinge. Don't get too confused about it. I mean, I build it in because I sometimes see that students are confused about this initially, but that's of course what we want to learn. And we want to learn that it's not really that different. So just do intuitively what you would do if the force, the distributed force, would not cross through the hinge. So there's nothing special you need to do. I know that students are sometimes confused about the fact that it goes through, but just release the system either on the right side or on the left side, and just include everything to the right or to the left. You also have this force on an angle, so that of course means that there must be a horizontal component, and hopefully you can identify where that has to be resisted and you can calculate that properly. That is problem number B. Let's move on to problem number C, which is here, and it's given not as a image, it's actually given as an engineering representation. So you can clearly see that here you actually have a pin, and here you have a roller and a roller. The hinge is right here. And I don't think there's much I have to say about this. Hopefully you can already see which support reaction you should calculate first. There's no right or wrong in terms of which one you should do first, but there's one that is easier and there's other ones that are more difficult. And if I would tell you anything more, I would probably do your work for you. So I wish you good luck with that. Last but not least, we have a problem that includes a concentrated moment and a distributed force. And we have pretty much a simply supported beam with overhang that is then connected to yet another support here, which you can consider this also a simply supported beam. So there should not be much confusion here, but if you need clarification, you know how to reach us and how to get clarification. For now, you are the lucky ones who only have to deal with 4 problems here. In the future, I obviously need to add 2 more problems down here to distribute the workload better. But right now, you are welcome to have such an easy semester where you can spare so much time. I wish you good luck on solving this homework problem, and I will see you for the next lecture. Until then, stay safe.